Hi, my name is Amira Abbas, and I am super excited to talk to you today about quantum computing, quantum circuits, and how it fits into machine learning. So let me share my screen. I wanted to try and learn a little bit of Portuguese for the talk today, but I will not embarrass myself and I will just stick to quantum computing for the moment. Okay, so firstly, thanks a lot to the Data Science Portugal team for inviting me to speak. I'm really happy that other people also believe that quantum computing will play a large role in the future of machine learning. And what I'd like to do today is to show you, so I'm assuming that everybody watching this is from a machine learning background. And so what I'd like to show you is that quantum circuits can be thought of as mathematical objects which you are very familiar with. So they can be framed in terms of vectors, of matrices, and of tensors. And in this way, you should be able to get a high-level understanding of how quantum circuits work and understand a framework which I present of how we can think about using these quantum circuits in a machine learning context. So it's really not to give you too much of a rigorous mathematical definition, but more just a high-level understanding of the intuition of how we like to use these quantum circuits in a machine learning setting and why. Why do we do this? But first, we must cover the basics and we must understand quantum computing. So it's kind of become a buzzword and you see it everywhere in pop science, right? And in movies. And while it's nice that science is becoming popularized like this, but it's very often accompanied with a lot of false claims. So, for example, quantum computers will break all encryption. Definitely not, right? Unfortunately, they will not solve all our problems either. And in my opinion, I don't think they will replace all classical computers. But we still look at them because they offer us a different way to do computation. And this is what I'll talk about today. And a large reason why we're looking at quantum computing is because we kind of have to. We have to have some sort of different architecture proposed because we are hitting boundaries with our classical hardware as we have it now. So what you're looking at here, if you just look at the blue dots, is the number of transistors on a given chip, and this given chip is a fixed size. And since this is linearly increasing on a logarithmic scale, what this means is that as time progresses, the number of transistors are doubling. And this is very much in keeping with Moore's law, right? Where the number of transistors roughly double every 2 years. And for those of you who don't know, transistors are just these things on computer chips, these tiny little things that can be either switched on or switched off. So they can be in state 1, state 0. And this is like how you encode binary information. And so the more transistors you have on a chip, then theoretically, the more information you can have encoded onto a chip. And so more transistors means more computational power. Okay, but as I said, we are approaching a limit, right? So we're actually approaching atomic scale where these transistors are becoming as small as the atoms that are used to make these chips. And this is problematic because when we start to look at really, really small scales, then the classical description of physics as we have it starts to break down. And so there are other proposals for different architectures for computation. I won't speak too much about them, but one of them is like this 3D hybrid computation. I think you will actually see in your morphic computing talk today, if I'm not mistaken. And then, of course, quantum computing. And the reason I like quantum computing a lot is because, as I said, when we look at these really small scales, then our classical description of physics starts to fail. And the reason is because at these very small scales, we start to observe quantum mechanical effects. And this is where quantum mechanics becomes important. And the accurate description of physics at this very small scale is quantum physics. And so really awesome physicists, like Richard Feynman made these proposals where he argued that nature is in fact quantum, right? And if we ever want to accurately model nature, we have to incorporate quantum mechanical effects. We have to have some sort of understanding of how quantum mechanics comes into play. And so physicists and engineers and computer scientists got together and they were like, okay, well, instead of letting these quantum mechanical effects destroy our computation, why not try to build something that actually harnesses these things and allows us to do quantum computation? And so this is one of the motivations for quantum computing. Another motivation and another reason why I think it's really important to look at quantum computing is because of the exponential Hilbert space that a quantum computer can enjoy. And this, to make this understanding a little bit clearer, then we have to talk now about qubits. But before we can talk about qubits, we quickly revisit classical bits, right? So as I said, transistors can be either switched on or off, and these correspond to classical bits of information, zeros and ones. And if, for example, we had 4 classical bits, then one possible combination of these bits could be that 0, 1, 1, 0, yeah? Another one, quite obviously, could just be if all these classical bits were 0. And if we look at all the possible combinations of zeros and ones for these 4 classical bits, we have this many. But what's important here in a classical setting is that these 4 classical bits can only occupy one of these combinations. And that's the key difference between classical computing and quantum computing, because in a quantum computer, we can, if we have 4 qubits, we can create a linear combination of all possible states that these qubits can occupy. And this is where the exponential Hilbert space thing comes in. Because if you look at all possible combinations with 4 qubits, it's 2 to the 4 possible combinations that we can have coexisting. We can have a linear combination of all these bases, we call them basis states. And a very common slide that's often used to demonstrate the potential, the power of quantum computing is this one. I like it quite a lot. So it says that if we had just 275 qubits, then that gives us 2 to the 275 possible states that we can represent on a quantum computer. And this is already more than the number of atoms that we see in the observable universe. So this is a huge, huge amount of space that we can work with just 275 qubits. Okay, so now we understand the motivation for quantum computing, and it's time to look a little bit into the mathematics and understand what are these objects so that we can put them into a machine learning framework. So let's look just at 1 qubit. And 1 qubit gives us 2 possible basis states, right? So 2 to the 1, 2 to the number of qubits, tells us how many possible states we can have. So 2 to the power 1 gives us 2 possible states. This makes sense because we know 1 qubit can either be 0 or 1. And when we have a linear combination of these possible states that it could be in, this is what we call a state of superposition. So you must have heard this term if you've heard about quantum computing. And all superposition is it's a linear combination of possible states that a qubit or multiple qubits can be in. But what makes it special is the properties of these coefficients, and I'll explain mathematically what these quantum states look like. So we actually write this in quantum computing in this way. And what these pipes and angular brackets are is it's something called Dirac notation. So anything in these pipes and angular brackets can be thought of as a quantum state. It's called a ket vector. But before we go into that, this symbol here, psi, just represents our state of superposition. And what this is saying is our state of superposition is a linear combination of the quantum state 0 and the quantum state 1. And these coefficients are just numbers, right? So they're creating a linear combination between 0 and 1. And in fact, the only restriction of these coefficients, of these numbers, is that the sum of their absolute value squared needs to equal to 1. And if we try to understand a little bit deeper what these coefficients mean, they actually correspond in a way to probabilities. So this number here, this alpha 0, gives us a little bit of information on how likely it is for our superposition state to be in state 0. And alpha 1 gives us information on how likely or how probable our qubit is to be in state 1. And so you can view also a state of superposition as a probability distribution over different states. So if we have 1 qubit that's in superposition, well, then there's a probability distribution that describes how it looks, how probable it is to be in state 0 and state 1. But with one very important caveat. So the probabilities are actually the coefficients, absolute value squared. So if we take alpha 0 squared, the absolute value squared, that is the probability that the qubit's in state 0. And the absolute value of alpha 1 squared, that is the probability that the qubit's in state 1. And the caveat that I mentioned is that these coefficients can actually be complex. They can be complex values. And this is a crucial distinction between a probabilistic computer and a quantum computer, because one can still argue that, we can take classical bits, we can make them probabilistic, right? We can create linear combinations and probability distributions, but these probability distributions are classical. The numbers that have to go here have to lie between the real line, between 0 and 1. But on a quantum computer, these numbers don't have to satisfy that. They can actually be complex. And this is what makes them mathematically interesting and different. Okay, so I spoke about the coefficients, but now what do these quantum states look like mathematically? What are these ket vectors? Well, you might have guessed from the name ket vector that it is just a vector, right? So we represent the 0 state as this vector, 1 and 0. Why? Well, you can kind of think of it as like a one-hot encoding strategy, where the first entry corresponds to 0 and the second entry corresponds to being in state 1, yeah? So what this ket vector is saying is that the 0 state is in the 0 state. It's 100% in the state 0 and 0% in a probability that it's in state 1. Okay. And then obviously the 1 state will kind of be the opposite, right? So if we stick with this one-hot encoding analogy, well, then it's definitely not in state 0 and it's definitely in state 1. And so a superposition state is basically just saying we take alpha 0 times this ket vector and alpha 1 times this ket vector. And then we have a vector representation for our state of superposition, which depend on these coefficients. So a qubit is just simply a vector, and that's all you really need to understand. And I think it will become a little bit clearer as we scale up. So let's look now at 2 qubits as for an example. So with 2 qubits, we have 2 to the 2 possible basis states that we can have, right? So if we write now our state of superposition between all of these states, well, we have, with 2 qubits, we can have 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then we have 4 coefficients. And so now if we look at this ket vector, how would we describe 2 qubits? Well, we actually just take the tensor product of the 0 vector. So remember I said the 0 ket vector is just 1, 0. And if we have 0, 0 here, then it's just the tensor product of 0 and 0. And this gives us this ket vector. We take the tensor product of these two things, it gives us this. And this again falls into our one-hot encoding strategy, right? So our analogy. So this first entry of the ket vector, it kind of can be viewed as is the state in 0, 0. Is it in 0, 1? Is it in 1, 0? Is it in 1, 1? And so this one here that we look at is definitely in state 0, 0, which is why it has a 1 here and 0 everywhere else. And similarly, this would be the tensor product of 0 and 1. This would be the tensor product of 1 and 0, and this would be the tensor product of 1 and 1, and that gives us these ket vectors. And then, of course, our superposition is just, again, a linear combination, right, of these ket vectors, and we can represent them in terms of these coefficients. So if I give you, then, this state of superposition, and I write it like this, as beta 1 times 0 times this quantum state here, which has 0, 1, 0, and then beta 2 with this quantum state 1, 1, 1, you should immediately start to notice certain things. You should immediately see, okay, well, there are 3 qubits in my system that I look at, because the quantum states here there are 3 qubits in this. And the ket vector, you should also be able to start to describe this ket vector, because we know that this ket vector here will be the tensor product of the 0 state times 1 times 0. And then this one here will be the tensor product of just 1, 1, and 1. And then our superposition vector would just be the sum of these two things times by beta 1 and beta 2. If this is not making too much sense, then don't worry. All I want you to see or understand is that qubits are vectors, single qubits are vectors. And then as we include more qubits into our quantum system, then we just take the tensor product of vectors. Okay, so now we talk a little bit about the circuit representation. And if we consider, again, just one qubit in our system, then we can draw a quantum circuit like this. So this is saying that our initial state is 0, and this one wire here means we have one qubit in our quantum circuit. And now let's say I want to do something to my qubit in 0, such that when it comes out of whatever I do to it, it's now in the 1 state. So I want to go from the 0 state to the 1 state. I want to manipulate this qubit and turn it into the 0 state, into the 1 state. Okay, so this is now where matrices come into play. So if we want to manipulate qubits, all we need to do is start to multiply matrices on them. So here, this is something called an X gate. An X gate in quantum computing has a matrix representation, and it looks like this, 0, 1, 1, 0. And if we take our X gate and apply it to our original state, so let's look at the circuit diagram here. We're saying we're starting off with a qubit in state 0, we're applying an X gate, and I argue that we get out the 1 state. Let's look at it mathematically. Well, we have a vector, we apply an X gate, and what we get out is the 1 state, which is exactly what we want. So this here is the ket vector representation of the 1 state. Okay, cool. So actually, if we have a qubit and we apply some matrix operator on it, we call this an operator, then we can start to create arbitrary quantum states. We can start to create states in superposition and so on. And so this is how we manipulate qubits, by simply applying matrix operations to them. Okay, and so remember I said as we start to add more qubits into our quantum computer, into our quantum system, well then this is just taking the tensor product of these states. And then here we can start to apply different matrices on these qubits and start to manipulate them, start to rotate them, start to flip them, and so on. And so one example is how to create entanglement between two qubits. Well, these have very specific operation orders. So if, for example, we want to entangle qubit 1 and qubit 2, then we apply something called a Hadamard gate and a C0 gate. And so what I want to show you is that we can have matrix operations that act on 1 qubit or 2 qubits or multiple qubits. And some examples of these matrix operators, we already did the X gate here, but this is how the Hadamard gate looks. And this actually puts a qubit in superposition. And here the C0 gate actually acts across 2 qubits, right? So it has a higher dimension, the matrix. And so these are examples of how we start to manipulate our vectors, our state vectors, and start to do interesting things with our qubits. And one more thing I should probably say, just for completeness, is when we start to then observe the qubits, the states of the qubits, very often I get asked, like the quantum state will then collapse, right? It will collapse to 0 or 1, and this is all you can ever get out. Yes, that is true, but if you repeat your observation, if you repeat your circuit and measure multiple times, so if you look at your output of your circuit multiple times, what you can start to get is an expectation value. You can start to get a distribution of how your qubits would actually look. So remember I said that your qubits can be in a state of superposition, which can kind of be thought of as a probability distribution over different possible states. If we then repeat our circuit over and over, we can start to extract this probability distribution by getting expectation values of our qubits. Okay, and then I say very quickly that quantum computers are real. I make a statement about hardware, even though I'm a theorist, but they are very much being built. We have one at IBM, of course, and we have a few actually at IBM. And these are available to you via the cloud. So I encourage you to try them out and play around with the software and manipulate qubits and stuff like this on your own. It's really cool. Okay, so now finally we can get into quantum machine learning and the notion of quantum machine learning. And I hope that I'm still good for time. So quantum machine learning is very often put into this paradigm of 4 topics, right? Where you have this interplay between classical data and quantum data, and a classical processor and a quantum processor. And so when I speak of quantum machine learning, I'm talking about this red block here, where we have classical data, as we do in machine learning, and this classical data is somehow integrated or processed with a quantum computer. And this is what I refer to as quantum machine learning. Okay, so how can we think about quantum computing, quantum circuits in a machine learning framework? Well, very simply, right? So let's say we start off with this initial system where all our qubits are in state 0. And so now we need a way to encode our data, classical data, into our quantum computer. We need a way to encode our information into a quantum state. And to be honest, there is no real rule on how to do this. It's actually still an open question which researchers are investigating. But I will present a few options to you just to try and explain the intuition. So we would have definitely some matrix operations in here that somehow encode our information. So let's say, for example, we had one data point that we wanted to encode, and we can represent this data point in a binary way, in a binary fashion, 1001. Well, then it's kind of straightforward to encode this information, right? Because we start off in the state 0000, and to get it to 1001, we simply can apply an X gate here and an X gate here. And now our quantum state, if we look at it after these X gates, would correspond to our data point. But if we had a data point that actually looked like this, right, with a vector with 4 entries, so it's a 4-dimensional data point, and we wanted to encode this information into our quantum circuit, well, we could have a matrix acting on the first qubit that depends on this value of the data point. And so we kind of rotate that qubit by 0.529, for example. And we can do the same thing to the second qubit, the third, and the fourth. We can make the operations in the circuit depend on the data values. And this is something called angle encoding. I should probably also say this is something called basis encoding. And this is a strategy called angle encoding. And it essentially is as it sounds, right? You're encoding the information of your data into angles. And basis encoding, you're encoding the information into basis states. And I encourage you, by the way, everything I say, there are often resources that I put here at the bottom left. This is a really nice paper to try and understand how to do data encoding, and this can also be compared to support vector machines in machine learning, where support vector machines do feature maps, right? So it takes your data, often maps it to a high dimensional space, and then does classification in the space. And if we take classical data, we embed it into a quantum state, this already corresponds to a feature map as we do in support vector machines. So this is quite a nice analogy that this paper talks about. Okay, so once the data is in, the next step, of course, is to build a model, like to have some sort of classifier or some sort of parameterized model, right? So we need some operations now that depends on some parameters theta. So we'll call this a parameterized model that's in the circuit. And again, of course, these are matrix operators that can depend on some parameters. So I just put them as like single, acting on single qubits, but this could be acting on 2 qubits, on multiple qubits. But the key thing is that these operators, they depend on some parameters, theta. And then lastly, we observe our system, right? So once we encode our data, we have some parameterized model that follows it. Then we can observe, we can measure our system. And depending on what our system measurements are, we can do some post-processing to get something that we can interpret as a label or a prediction. So for example, if we measure multiple times our circuit and we get an expectation value for our distribution, let's say our expectation value tells us that the most probable combination of states that we'd get is 0, 1, 1, 0. Then we can interpret this as some sort of label. And this is it. This is basically the framework that we try to build quantum models with most of the time in quantum machine learning. There are other methods, but this is quite a common one. And when these circuits depend on parameters, they have a special name. They're called variational circuits. Okay, so then how do we continue putting this into a machine learning setting? Well, then if we have a label that's output from our quantum circuit, We can plug this into a classical cost function, just as we do in machine learning. We can then figure out how to update our parameters and then update them in our circuit and rerun this loop until our cost function is minimized, just like we do in neural networks, just like we do classically. So we can start off with an initial guess for this parameterized circuit. We can get a label, we can put it into our cost function, and then we can start to update our thetas in our circuit such that it gives us a better output. And then we can use this trained circuit as a model, as a quantum machine learning model. And this is actually proven to be very successful in things like the variational quantum eigensolver. And here is again a source where you can read about it, but basically the VQE, the variational quantum eigensolver, is often used to solve very complicated combinatorial problems. So one of those is like the traveling salesman problem. And VQE has been really successful and excitingly on hardware that we have today. So these variational circuits can work right now on the quantum hardware that we have, which is what makes them quite cool. And all VQE says is that we have some very, very complicated combinatorial problem, which we can encode in something called a Hamiltonian. And this Hamiltonian will depend on some parameters, okay? And this Hamiltonian basically represents the energy of our system. And when we want to minimize this energy, when we want to find the ground state energy, this corresponds to the best solution in our combinatorial problem. And it turns out that putting this Hamiltonian that depends on parameters into this parameterized circuit framework and using cost function minimization gives us a really, really nice way to estimate the minimum eigenvalue, which corresponds to the lowest energy state. Okay, but if you are a machine learning person, you might then be thinking, but how on earth would we update these thetas? Because this would involve, normally with backpropagation, we try to calculate the gradients and use these gradients to update our thetas. And you're totally right in hesitating about this, but a very, very nice result from, again, this paper here shows us that we can calculate gradients of quantum circuits with respect to parameters by something called the gradient shift rule, the parameter shift rule. And so if we take our circuit and we run it with parameters and we shift those parameters up, and we take the difference of that circuit with this circuit where we shift the parameters down, this corresponds to the gradient of a quantum circuit. It's quite a beautiful result and very much looks similar to the finite difference rule. Okay, so that is basically the framework for quantum machine learning, right? We have some data. We figure out how to encode this data into a quantum computer, where we then do some processing with our parameterized model. We make a measurement to get a prediction. And then we do this again. We plug this prediction into a cost function. We figure out how to update our parameters and so on. And it really can be as simple as that, right? Because remember, our input state is just a ket vector. We then apply some matrix operations to this, and these matrix operations need to incorporate encoding our data, and they need to incorporate some parameters. And then we measure to get our prediction, as we do in a classical sense, we need a prediction. And then we optimize this classically using a classical cost function. And so if you're interested, I encourage you to check out these free resources. This is a book on quantum computing, I think. I should have put some labels here. But this quantum algorithm zoo is really amazing. It has a whole bunch of already proposed quantum machine learning algorithms up there. QoSF, the Quantum Open Source Foundation, is beautiful. They collect open source free resources for you to learn quantum computing. They also have really nice mentorship programs. The Qiskit textbook, of course, is a really cool one. Qiskit is an open source programming language in Python for you to do quantum computing. And then Microsoft also has this really nice documentation called Katas on their GitHub, which is cool. And then I'd like to just leave you with some open questions, right? Because this is what we are doing now in quantum machine learning. We're trying to understand what makes a good model. I presented you with a framework of the circuit, but we still don't understand so many things about the circuit. We don't understand how to embed our data properly. We don't understand why certain circuits work better than others in certain machine learning tasks, and how entanglement concretely affects a quantum model. This is not, I don't think this is answered, and the complexity of these models, how do they compare to those classically? And this is actually what I'm trying to do my research on. And the promise, of course, I mean, quantum computing and quantum machine learning has already demonstrated quite a lot of useful applications. But the promise is that like they could potentially disrupt a lot of industries, right? So in financial markets, there is a lot of randomness in markets, and people often argue that one needs a quantum computer to model these very complicated interactions. In AI, we spoke about this. Quantum machine learning could perhaps augment and help and build stronger algorithms or different ones. And where I think, and I think a lot of people would agree with me, the largest impact we will make with quantum computing and quantum machine learning is in quantum chemistry and in chemistry in general, because of things like material design, and we can start to look at like creation of new medicine and understanding interactions which we just could not model previously. I mean, some interactions between molecules are just so complicated that we cannot even begin to simulate them on the hardware we have with classical computers. So how can we start to dream about studying them, right? And now with quantum computers, we finally can. Okay, and I think I've talked enough now. So thank you very much for having me. Please feel free to email me if you have any questions, or reach out to me on LinkedIn or Twitter. I will make these slides available somewhere.
All right, guys, welcome back. So first of all, thank you for all the questions that we've been already getting. Keep on posting them. If you don't have any question, just go there and vote for your favorite questions. So while we proceed with the first introduction, and welcome Amira to the live streaming. How are you doing?
Hi, I'm very good, thanks. Thanks for having me.
All right, before we start with the question, let's get this big elephant out of the room. So my sources tell me that you're a great self-proclaimed rapper. Is that true?
Yes, it is definitely true. Self-proclaimed, yes. Very good rapper.
All right, let's do it this way. I'm not going to ask you to rap here because I don't know how confident you are about it, but maybe let's just share what's your favorite artist. Which one do you like to rap the most?
If I could have, I definitely won't, because I promised my colleagues I wouldn't embarrass myself on a live talk. But if I could have, it definitely would have been some Eazy-E, maybe some Farside, some Notorious B.I.G. I really like old school hip hop and R&B.
Awesome.
So yeah, so if you ever catch me in a karaoke bar, then yeah, I will do this for you.
If you're ever in Portugal, well, Belgium in this case, let's do that. All right, but also when I was reading your bio, it was very interesting. I saw something interesting and quite in common with us organizers here at the SPT, is that you're also active in tech communities in South Africa. Can you tell us more about it?
Yeah, sure. So we also have something very similar to Data Science Portugal in South Africa and in Africa in general. It's called the Deep Learning Indaba. And it's just a community driven thing that tries to strengthen machine learning and artificial intelligence education. And so I helped organize this event last year, and then I'm just very active in this community. So we very often give talks around machine learning, and now recently around quantum computing. And we also host seminars and breakfasts and just all these events trying to educate people in Africa.
Awesome. Well, if you go live, if you go online this year, do share the link. We'll be much more very happy to share it also amongst our community. All right, let's jump into the questions. The first question is quite a simple one and could be interesting. So what do you suggest to a student that wants to pursue the field of quantum computing combined with machine learning? Where could they start?
Yeah, it's a good one, because I think it's a little bit difficult, right? Because there is no clearly defined quantum machine learning field in curriculums yet. So I always like to say, strengthen your linear algebra, right? So quantum computing requires a lot of linear algebra, and this is also very popular in machine learning. It also requires a lot of linear algebra. So definitely strengthen this. And then there are free courses you can do if you don't come from a physics background, like the MIT and Stanford courses on quantum mechanics. The undergraduate courses are available online. So this will give you a nice background in quantum mechanics, and you have linear algebra, and then you can start reading about quantum computing and quantum machine learning. And so I think this is a nice place to start. And then I can also just recommend one more book called Quantum Computation and Quantum Information by Nielsen and Chuang. This is like the Bible in quantum computing. So if you're interested, then I strongly suggest reading that as a student.
Okay, sounds very cool. I hope this helps out a lot of people who got interested by your talk. So the next question, it's about actually the application of QML. So the question is that, are there any application that can beat the traditional machine learning, deep learning algorithms currently or not?
Yeah, so it's difficult because we don't really know how to define what's better, right? What is it meant by beating an algorithm? Does it mean a faster runtime? Does it mean a different way to process something, or to have a different way to calculate something? So if we mean speed ups, then yes, definitely there are many theoretical algorithms, theoretical quantum algorithms that are faster. But of course, we don't have the devices yet that are large enough to execute these algorithms, right? So there's that problem. But then there are also different algorithms that show a lot of promise. And one of them I think I mentioned just now is the support vector machines. And support vector machines are, I feel like they are just made to be run on quantum computers because you can instantaneously like compute kernels, which are often a bottleneck in classical computation. And so there's a lot of promise here on quantum kernels. And if you're interested, I strongly suggest reading. There's a lot of theory around quantum kernels and quantum support vector machines. I think this is a really promising application.
Okay, really cool. Maybe just a real quick follow-up question on one of the things that you said. So you said that the quantum computers are not big enough to currently go faster than the traditional machine learning algorithms. When do you think they will be, or what's your opinion on it? Or like, just, you don't need to give a straight sense of time, because I think it might be a bit
Sure.
hard since we're still such in the beginning, but maybe you already have an idea of what are the main things we need to achieve to get there.
Yeah, so I should have also maybe mentioned a little bit more that, quantum computers that we have right now, they're very noisy. So even the algorithms we run right now are still subject to a lot of noise and interference, right? And it's really difficult to say when we'll have these fault-tolerant quantum computers that can do all these wonderful things that we want. Because just a couple years ago, nobody even thought we'd have qubits at all. And so it just takes like one innovation to shoot us into the into this like really advanced place. And if I think back to old quantum, like old computation, old computers, right, I think they were built with like vacuum tubes. This was like the original
Yeah,
proposition,
yeah,
and error
those
correction.
big rooms with a lot of servers, and yeah, my mom
Exactly,
used to
right.
do that. Yeah,
And then your mom probably knows about error correction, right? Because they would
yeah.
like manually take them out, change them when they break down. And this is really bad. And then it just took one innovation, the transistor, and this changed the game. So I feel like it's really difficult to say when these quantum computers are going to have this, but it could be tomorrow, it could be in 20 years, it can, yeah, it's a hard one, but I hope very soon, because a lot of people are investing a lot of time, a lot of resources, a lot of money and research into this. So yeah, let's see.
Okay. So then maybe, as we were talking about applications here, and this is also kind of the top question, is that do you think quantum computing will be the key to simulate cosmological models and help some of the most important problems in physics?
That is such a beautiful question, and I desperately want that to be true. I want to say yes, and the reason why I would say yes is because nature, like I said, is 100% like has to include quantum mechanics, right? I mean, things that we observe and experience, it has to include quantum effects,
Hmm.
and cosmology and all of these wonderful physics things that get us interested in physics and asking all these lovely questions. It has to incorporate quantum computing. It has to incorporate something that can handle this quantum mechanical modeling. So I definitely think so. And but I'm not a cosmologist. I don't know for sure, but I think definitely. Yeah.
But I also think that, and this, I think you talked about this in your talk, that it's just that nature is not ones and zeros, right? It's somewhere in between. So if you can get a system that approximates to this, not ones and zeros, but this multitude of stages, then I think it makes also things a bit more, let's say, real life modelable. I don't know if that's a word.
I think
um,
so.
so one more question. So before we were talking about this, how long do we need to get to point of having, like, let's say, an increase in performance in quantum machine learnings, and when will they beat the classical machine learning models? But then maybe a really cool follow-up to question that we have from the public is, what are the major difficulties in implementing this type of circuits in physical hardware? And we know that we're just discussing it right before this talk. There are different types of hardware. So maybe you can give a bit of background there. That'd be nice.
Yes, sure. Maybe I'll start with a disclaimer that I'm a theorist and not a hardware person at all. But so take what I say with a pinch of salt. But so maybe it's good to say that there are different ways to build a quantum computer, right? So there are different hardware, and everybody is trying something new and something different. And so we don't really know what this eventual big quantum computer, this powerful one, will look like. But for example, the ones that we have at IBM that are freely available online are these superconducting qubits. And superconducting qubits make use of electrons. And the problem here is you have to cool these electrons down to very, very low temperatures so that you start to get these quantum mechanical effects in these electrons so that you can manipulate them for computation. But to cool things down to these low temperatures is a really difficult task. So this is the main hurdle there.
What kind of temperatures are we talking about? Just for people
to absolute zero.
Yeah,
Yes,
absolute zero. Is it? I don't think it's physically even possible, right?
It is not. Yeah, it would defy thermodynamics and physics as we know it. But we get very close. So I'm not sure the exact temperature, but I know that we have temperatures in our lab that are colder than outer space.
Okay,
so
wow.
yeah, it's pretty cool. But then there are also other quantum computers that don't require this, right? So there are some that operate on they use photons. So photonic quantum computing is another suggested way to build one, and this can be done at room temperature. But then there are other problems with photonics as well. Like people, it's unclear how they will scale, how we will get more qubits, and how many would fit on a chip. So there are size issues there as well. But I encourage you to Google and check yourself, like different types of hardware. So it's exciting to see, but the answer is we don't know. And what the problems are or how we can overcome this. I mean, this is a massive field in quantum computing now. A lot of research is going into this, right? How do we reduce the noise from our circuits? And a large way in which this is being mitigated, the errors, is through quantum error correction. But we need more qubits to do error correction. So it's a very strange battle, and it feels like nature doesn't want us to do this, but I feel like there will be some sort of hurdle soon that we will overcome. Yeah.
Interesting. All right, I think that's all the time we have. I think we're even a bit over time. So Amira, thank you so much. I just want to make a small announcement that also Amira is going to be at the SMBQ summer school, which is organized actually by the Faculty of Sciences at the University of Porto. I will post the link in the feed, which you'll be able to check in the platform in a couple of minutes. But I think it's going to be a very interesting summer school. It's on quantum machine learning, if I'm correct, and it's 2 days. He's also going to be actually a lecturer there. So do join. For sure, I will be there. Amira, again, thank you so much.
Thank you for having me. I did. Thank you.